He's working on climate change mitigation, soils, agriculture, food systems, ecosystem services, and modeling. He's been author of many reports of the Intergovernmental Panel on Climate Change, the IPCC, which has been awarded with the Nobel Prize in 2007, and contributed to it by the work of climate change mitigation, agriculture, forestry, and land for the 4th and 5th assessment report. As I said, his work is well received. If you count these numbers, his age index exceeds 100. He's cited several 10,000 times. He's been awarded for his outstanding contributions to climate change mitigation. He's won the Duchaufour Medal of the European Geophysical Union, the EGU, and is a fellow of several organizations like the Royal Society of Biology, a fellow of the Institute of Soil Scientists, a fellow of the Royal Society of Edinburgh, foreign fellow of the Indian National Science Academy, a fellow of the European Science Academy, fellow of the Royal Society. I hope I kept the hierarchy and did not, possibly there are many more. So we're happy to follow your presentation on challenges for measurement, reporting, and verification of soil carbon change for atmospheric greenhouse gas removal. Pete, the floor is yours.
Thank you very much, Wolf. So today I'm going to talk about what we need to do, what the step change that we need to make in measuring, reporting, and verifying soil carbon change if it's going to form an effective solution for greenhouse gas removal. So the reason we're interested in it is because soils have a large technical potential to remove carbon from the atmosphere. So the technical potential is estimated to be around 1.3 gigatons of carbon equivalents per year. And the economic potential, if we just look at the low cost options, would be between about 0.4 and 0.7 gigatons of carbon equivalents per year. So it's not insignificant. It can form up to about 10% of current emissions. The technical potential, at least, is to remove 10% of current emissions. The economic potential is lower, and the feasible potential is probably still lower. But nevertheless, it's an option that we have all over the world in all of our managed lands, which has quite a significant and large potential. You can see this is a slide from Paustian et al. In 2016, which was called Climate Smart Soils and was published in Nature. And this looks at the area of practice that's adopted. So this is the area up the vertical axis. On the horizontal axis, it's the average greenhouse gas emission reduction per hectare, the removal rates per hectare per year. So you can see that histosols, so these are our peatlands, have a very large per area mitigation potential, somewhere in the region of 50 tons of CO2 equivalents per hectare per year, but there's a relatively small area. And for some of the practices that we can consider, such as cropland management and grazing land management, we have vast areas, but they have a relatively lower greenhouse gas emission reduction potential when expressed on a per hectare per year basis. But combining all of these together, we get to the areas and the potentials. We can get to this figure of about 1.3 gigatons of carbon equivalents per year. And the other reason that it's that soil carbon sequestration is attractive is because we've been managing our soil just about from the dawn of agriculture, 10,000 years. So we know how to manage our soils and we know how to manage them differently. And if incentivized properly, farmers can easily adapt to different management practices that can better store carbon in the soil. So we can, for example, we can look at the baseline condition. If we've got degraded land, we can convert it to perennial vegetation. If we've got drained, cropped histosol or a peatland, we can restore it to wetlands. And then we have the other soils. If you've got nutrient deficiency, we can add nutrients. If we've got extensive bare fallow, we can grow cover crops. We can control the intensity of the tillage We can look at our nitrogen management. We can look at returning residues to the field. And there are a bunch of other things that we can do. We can add other organic amendments, such as municipal composts, farmyard manures, and those other aspects to increase the soil carbon sequestration compared to the current situation. So for just about every soil in the world that's under cultivation, there are some options that could increase the soil carbon sequestration. And because of the vast areas, there's quite a lot that we could do with soil carbon sequestration. So why aren't we doing it now? If it was so great, we'd surely be doing it now, wouldn't we? Well, there are a few drawbacks, a few potential pitfalls that we need to consider. The first one is that biological carbon sequestration and soil carbon sequestration, in this case, is not unlimited. So what happens is you have a management change here at time 0, and you get a change in soil carbon over a time spell. Say this is 5 to 10 years, you get a large increase in carbon stock, and that's removing carbon from the atmosphere. So you've got this level of removal. Moving forward, the same time step, that successively we get these get smaller and smaller. So the net annual removal is smaller, still smaller, till eventually we get to a new equilibrium position with the soil, and thereafter it no longer removes carbon dioxide from the atmosphere. So the carbon in is exactly equal to the carbon coming out, by definition of the terms of equilibrium. So we have a saturation issue, which means that we can probably manage the soils to increase the carbon stocks, but only about between 20 and 100 years at these northern latitudes in Northern Europe. Then that tends to be around about 50 years. So we can increase the soil carbon for 50 years, after which we're no longer getting a net annual removal, but we still have to maintain the same practices. So saturation is an issue. We can use soil carbon sequestration to get to net zero by 2050, which is only 30 years away. But if we're looking at longer term solutions, we need to think about others. Nevertheless, soil carbon sequestration is a really useful option for sequestering carbon whilst we're decarbonising all the other sectors of the economy where we need to reduce greenhouse gas emissions immediately and aggressively. The second issue, which is not ideal, is that of non-permanence. So the carbon that is sequestered is subject to reversibility. So if you continue with a good practice up until saturation point, all well and good. But if you decide to change to, for example, low input crops, or if you're doing reduced tillage and then you start to do very intensive tillage, you can lose that carbon very quickly. So the carbon that you gain can rapidly be lost. So there's an issue not only of saturation, but also of reversibility. And lastly, there's the issue of additionality. So when we have a field with mineral nitrogen and manure added, if we remove that manure and put it onto this farm over here on the left-hand side, we're adding more manure, and we might measure the soil carbon and say, great, we're increasing soil carbon, so all is well. But by increasing the soil carbon, we've decreased it here because we've got less manure now going into the soil. So the effect over the whole cropland area is zero. So it's important that we account for all changes in soil carbon, not just the areas where we're doing a practice. We have to consider the impacts that has on other areas of carbon sequestration. So I'm just highlighting these things because sometimes people say soil carbon sequestration is great, there's no downsides. So we should really launch into it all of our efforts. And I think we should launch into it with all of our efforts, but we have to be aware of these limitations, which is the same with all biological things. So how do we measure soil carbon then? The first one is obviously we have direct measurement approaches. So we take samples in the field, we take many samples. Because of the heterogeneity of soils, we have to take many samples to get an accurate representation of the soil carbon. The gold standard is then to take those away, and we do dry combustion using a LECO analyzer shown here or some other form of CNN analyzer. These are automatic systems. which you prepare the samples, put them in, and then you get a measurement of the soil carbon that's held within the soils. But these are very slow, costly, and labor intensive. So for verifying soil carbon for every individual field that you're applying a management change to, it would be prohibitively expensive, and it would cost more to demonstrate the change in soil carbon stocks than the carbon credit that you'd get if you were selling those that carbon on the open market, on the voluntary carbon market. The thing that comes along then is an alternative to direct measurement is the in situ carbon sensing. So this is using things like Raman spectroscopy, visible to near infrared spectroscopy, and various other forms of spectroscopy. And these offer potential for rapid high resolution mapping of soil carbon. For example, these could be mounted on the back of farm machinery, and they can get fairly accurate representations of the variability in a field. But the challenges are that these are very difficult to calibrate. So the effects of varying soil moisture and mineralogy means that you can't get very accurate estimates of soil carbon as yet. And there's also the high cost, and the maintenance of the sensors is not insignificant. So whilst this shows some possibilities for the future, it's not something that we yet have the capability to do. And the last form of direct measurement is from airborne or satellite-based carbon sensing. So it's relatively inexpensive and there's global coverage, but it generally needs bare soils. So it's best for fallowed croplands. And where you have cover crops or a rotation where you're not leaving much bare soil, then you have real difficulties detecting anything that could give you soil carbon. It's not suitable where you've got vegetation or residue cover. So for example, one of the things that you might do is to increase your returns of residues to the soil. And that would mean that you couldn't then use remote sensing as a way of measuring soil carbon or estimating soil carbon. But it's really good for large area surveys and for mapping. So in terms of direct measurement, what we're aiming for is low cost estimates with a low bias and only low moderate uncertainty that we can apply at the project scale. So we need to have direct measurements, that these need to be fewer and of high quality so that we can calibrate our estimates and our models. I'll come on to this in a bit more detail later. We need a reduced uncertainty of the local scale predictive models. So I'm going to come on to this later as well. It's one of the components of a future MRV system. And we need to be able to incorporate farm level activity data. So that's information about what the farmer is doing on his or her field that may influence soil organic carbon. So the importance of being able to reflect real life information, real farm management information in the system is needed. So other than direct measurements, we need a comprehensive framework to look at how to measure, report, and verify soil carbon. This is the biggest barrier at the moment to using for gaining carbon credits for soil carbon sequestration. Lots of companies, farms, organizations are interested in developing these. So we've got some ideas about how we could go about setting up such a system. Before I go on to those, there are just a couple of other examples that I'll give you. This is a company that I've been speaking to in the US, Yardstick, and it uses a drill, just a standard drill with a sensor in the end that you drill into the soil, and it uses spectral methods to determine soil organic carbon. At the moment, it's not yet accurate enough to detect changes in soil carbon because of the small change relative to the large background. But it is, you can take a lot of samples relatively cheaply. And this is under trial. It's being trialed out in the US and elsewhere at the moment. And other examples exist. For example, these soil optics as a sensor bar, which is mounted on farm machinery that can detect the gamma radiation from these natural isotopes, and it can be used to match the soil. It doesn't do soil carbon, but you can imagine something in the future that would that would combine these technologies to give you estimates of soil properties that could then be correlated with soil carbon. So the soil monitoring and verification system. So I'm going to be coming back to this slide and we're going to be going through it in a little bit more detail. We're going to be taking them one by one. But in brief, I'll just talk you through it quickly at the moment. We have each of these individual components, 1 to 7, already in existence in many areas of the world, but we haven't put them together yet in a framework for MRV, monitoring, reporting and verification of soil carbon. So we have a bunch of long-term experiments and benchmark sites. You've got many in Germany, which have been running for decades, which measure changes in soil carbon under different management practices. So a network of these practices would be great as benchmark sites against which you can test your models and test your short-term measurements. Nested within those long-term experiments, you can have shorter-term experiments, for example, flux towers or chamber measurements, which can investigate the processes, develop novel tools, and to calibrate models. You've got your models over here, which are greenhouse gas models or soil organic carbon models or ecosystem models, which are developed using the short and long-term data. They're evaluated, and you can either use those to directly predict changes in soil carbon or to develop tier 2 emission factors. So emission factors that can be used with simpler methodologies to assess changes in soil carbon. But you can't use those models on a spatial scale unless you have the spatial data to drive the models. You also need the activity data. The activity data is things like the management data on the farm. When did you till? How deep did you till? What tillage practice did you use? Did you return the residues? That sort of information. But lots of these things are collected already in farm records. And we also need, we can also use soil resampling surveys. So many national soil surveys, including the one in Germany, has spatially referenced plots, which it goes back to every few years and measures changes in soil carbon. So we can use those as external verification of the predicted changes in soil carbon. And lastly, as I spoke about a little earlier, we've got the remote sensing opportunities, which you can either verify activity data. So for example, if a farmer says that they've left the residue on the field, you can probably spot that from satellite images to verify that that is the case. You can also estimate inputs, and you can also estimate some parameters to do with soils and vegetation. So let's look at each one of these in a little more detail now, and then come back to thinking about how we integrate them into a framework. All the time, I know that people in your department are working on robotics, artificial intelligence, machine learning, and a bunch of other technical issues. So I'd like you to look at this. I don't have the answers for some of these things, for many of them, I would say, but it may spark in your heads something where you think you could contribute to developing such a system. And there's a real need and a real desire to do this out there, and potentially from the private sector, some money to develop those techniques. At the same time as, so this was published in a paper that I published in Global Change Biology with a whole bunch of co-authors in 2020. At the same time, Keith Paustian was putting together a similar paper. I didn't know about his paper, he didn't know about mine, but we came up with more or less the same system. So it shows that convergent thinking, I suppose, in that we need a lot of the same things: spatial inputs, remote sensing, models, long-term experiments, land manager input, decision support systems. So he's arrived at the same, and I think he's got a much prettier diagram than I came up with for our paper. So let's have a look at the first one, item 1, long-term experiments and benchmark sites. Well, the good news is that there are already there's already a bunch of long-term experiments out there. These aren't really connected together in a network currently. So back in the 1990s, I was involved in putting together a network of long-term soil experiments called SOMNet, Soil Organic Matter Network. When the funding ran out, a group in the US, Dan Rector and colleagues in North Carolina, Duke University, took this over and developed it further. And now we've given it to the International Soil Carbon Network, but it's not an active network at the moment. It's just a database of experiments that we collected together. But what you can see is that there are quite a large distribution of long-term experiments around. These are long-term experiments looking at agronomic practices, and you can see we've got a distribution of these all over the world. These are tillage experiments, a distribution all over the world, particularly in North and South America. And these are land use change experiments, fewer of them, but still a few around. Most of them, however, occur in temperate zones, so in the northern and less so in the southern hemisphere, but we really have a scarcity of information in the tropics. So that's an area that we need to fill in if we're going to develop a global framework. In terms of shorter term experiments, we've got things like eddy covariance, and this is from the same paper, from a paper published in 2012, looking at what we need to develop a system to measure and report soil carbon. These are all the FluxNet sites around the world, and as you know, there are a great number of these, and a few more have been added to the tropics since this paper was published. But this is just an example showing an eddy covariance system. It measures fluxes of CO2 and other greenhouse gases into and out of the soil vegetation system. So you get direct measurements of ecosystem carbon fluxes, which can be very useful for calibrating models and for verifying any changes that you have in soil carbon. Item 3 are the soil organic matter, soil organic carbon or greenhouse gas models. What we can use all of the data to improve these models. So we've got a bunch of simple models, such as statistical regression models. We got some simple soil models, such as Rothsey and Ecos, and we've got wider ecosystem scale models that include soils, for example, DNDC and Century. This is an example from Century, but all of these represent soil carbon. We can use soil respiration data, long-term experiments, isotope data, flux data, and isotope pulse labeling data to improve the process description in the model. We can evaluate the model using statistical techniques. We've got lots of papers that do this to assess model performance. Then we can improve the description and go back and do this all again. So this is used to build confidence in the models and to reduce the uncertainty and to make sure that they work in all situations. So they're very important, and modeling plays a key role in this. I think maybe as well as these process-based models, we could think about using artificial intelligence and machine learning to synthesize some of this data and to assimilate some of this data to see if it could come up with reliable predictions of soil carbon change. This is just an example of the soil CNN routines in a pool model, this is the one that we use in Aberdeen. This is called Ecos, and it has coupled carbon on the right and nitrogen on the left routines, which are used to simulate CNN fluxes and greenhouse gas emissions from the soil. Here's an example of Descent, very similar pool structure. And this is an example, it's just another example. This is the DNDC model. But there are over 50 of these soil organic carbon models or ecosystem models out there that could be used, potentially could be used in such a system. The next one is that we need the spatial data to drive the models. So we need climate and soil data. So it's just some examples here of the organic carbon density, the organic carbon density and the land cover in 2010. So a bunch of these are freely available, but we need those. 10 years ago, I think this was something that we were still hoping for better data on. But now I think there's a range of data sets out there, the soil grids data, the Harmonized World Soil Database, lots of metadata available at different scales and temporal resolution. So I don't think this is any longer holding us up in progressing with soil carbon monitoring and verification. The one that's most difficult to get, I think, is the activity data. So item 5 is the activity data. In developed countries, we tend to keep good farm records. In developing countries, this isn't so much the case. But there are things like the farm management record books, which farmers in the EU, for example, have to keep for their single farm payments. A lot of this information is collected anyway. So can we find some way of linking these databases to the soil carbon models to drive them automatically so that all this data doesn't have to be re-entered? Remote sensing, I've already said a word about, but remote sensing can be used for collecting management activity data. So for example, we can see tillage and residue coverage. We can verify crop cover type or cover crop presence. We can look for flooding by using optical, spectral and hyperspectral images and also radar. And we can combine these to get really quite detailed maps that estimate parameters such as the activity data. And this could either be used to verify what the farmer has declared that he's doing, he or she is doing. So that could be, as a verification data to check that what is being reported is actually occurring, or it could even be used to collect data that you use to drive the models. And we could also use it for productivity surrogates. For example, we could use canopy N, growth photosynthesis, or leaf area index to calibrate models and to feed in with a data assimilation process to adjust the carbon inputs that are going into the soil, which give us better estimates of soil carbon turnover over time. And the last one is spatial soil resampling, which is done on a survey grid or geolocated positions, which are returned to after several years or decades. These give us good additional verification data. This is one example of one such study that occurred in the UK, where there were some samples in 1978, resampled in 2003, which reported carbon losses across soils in England and Wales. This was published in Nature in 2005 by Pat Bellamy and colleagues. So having said that we've got all these different components, we don't yet have a framework. We don't yet have a framework to pull all of these things together. And I think that's what's desperately needed, either at the country level, at the European level, and ultimately at the global level. So what FAO have tried to do, the Food and Agriculture Organization of the UN, is they tried to put a system such as this together. It doesn't contain all of the information. It doesn't link up with satellites. It doesn't contain all of the detailed information. It's largely based on modeling, but it's the start. So RecSoil is the Recarbonization of Global Soils project. And they have a part of this, which is called the Global Soil Carbon Sequestration Potential Map, or GSOC-SEC, Global Soil Organic Carbon Sequestration, which is used to define and allocate stock change factors, soil carbon stock change factors. So it's based on a range of spatial data sets, which are combined to estimate this change in soil carbon, some stock change factors that can then be used in country level assessments. So this is particularly useful in developing countries, which don't have necessarily the technical capacity, and almost certainly don't have the driving data that you would need to do a detailed remote sensing modeled framework, such as the one I described earlier. So in summary, there's great potential for soil carbon sequestration, especially in degraded croplands, but also, especially in croplands rather, but also in degraded pastures. There are many co-benefits for increased soil carbon levels, including climate change mitigation and adaptation, enhanced productivity, enhanced ecosystem services, and delivery of the UN Sustainable Development Goals. So all in all, soil carbon sequestration is a very good thing. But we have to remember that sink saturation, reversibility risk, and leakage risk are disadvantages compared to greenhouse gas emission reduction. So wherever we can reduce greenhouse gas emissions, we should do that, but we can use soil carbon sequestration to mop up any of those greenhouse gas emissions that we can't abate or that are difficult to abate. But in order to do that, we need robust monitoring, reporting, and verification. One of the biggest barriers to implementing is the challenge of MRB for soil carbon change, but I've just outlined a framework which I think could move us towards a situation where in the future, we could include soil carbon sequestration in useful projects for climate mitigation. And all components of that framework exist to some extent, but uneven globally, and they're not integrated. But I think FAO's REC Soil program is an opportunity to bring these together, especially in developing countries. There are some new non-destructive measurement techniques in development, so we need to watch and see how these develop, monitor their progress. As I said, they're not sensitive enough yet to detect changes in soil carbon, but they can give us a good estimate of baseline soil carbon, maybe. And in the context of this talk today, why I'm talking to you guys about it, is there are great opportunities for robotics, artificial intelligence, machine learning, data assimilation, and advanced modeling. So I think you will know much more about these aspects than I do. So hopefully this will spark some ideas about where you could contribute to this global endeavor, should you wish to. So thank you for your attention. I'll take any questions.
Yeah, thank you very much, Pete, for the very nice overview, which is now open for discussion. I suggest you just either raise hands. Yes, you see many hand clappings, but this is not question. You just raise hands or put just a note in the chat. Try to visit the chat and then we can follow it line by line. Who wants to start? There's the first from Gabriel. Gabriel, you want to place your question by yourself?
Yes, I can. Thanks for the great talk. Thank you, Pete. So I was wondering, so you mentioned this equilibrium at the beginning until which you have reached soil carbon sequestration. I just wonder, is the magnitude of this kind of fixed for certain soils, or what parameters are most important where this magnitude is reached? And then related to that, so if you for example think about crop breeding, would you say that increasing root biomass, for instance, will just simply speed up the time until which this equilibrium is reached, or will you also bounce this up, this equilibrium, until which then, to which extent you can actually sequester carbon into the soil?
Two good questions. Yeah, I think the soils are mainly, it's the soil type that mainly determines the equilibrium level. So it largely depends on things like cation exchange capacity, and the clay content is a really good indicator. So clayey soils can hold more soil carbon than very sandy soils. So even despite putting lots and lots of inputs into a sandy soil, it never really increases that much. So the best way to assess whether a soil can store more carbon is by its land use, really. So when a soil is taken out of native vegetation or out of long-term grassland, for example, it loses between 40 and 60% of its soil carbon. So a great target for soil carbon sequestration is our croplands, because they're depleted in soil carbon, so have the potential to gain soil carbon much more. There's less potential because they're closer to equilibrium from permanent grasslands. They tend to be high in soil carbon, so they're closer to the equilibrium position. Your question about plant breeding, I think by putting more root biomass in, I don't think you would increase the carrying capacity of the soil. You would just speed up the rate at which it gets there. What could change that is by breeding plants with more recalcitrant roots. So more lignin in the roots, or some other chemical compound that breaks down more slowly. That could increase the longevity of the soil carbon that's exuded from the roots or from root turnover, and that would stay in the soil longer. So that could really have a significant difference, probably more so than just increasing the root biomass. Very good questions. Thanks, Gabriel.
Thank you very much.
Thank you. Jan is next.
Yeah, thanks, Pete. That was a great overview. And as you know, I'm just a user of this kind of data, but I have a question related to user-generated data and whether that is at all an option. So we do a lot of surveys all over the world, especially in the places where your maps showed very low density of dots. And in those surveys, we visit farmers, we sometimes visit their fields. All these farmers have, or many of them have cell phones. I'm just wondering, is that at all useful for this, a circle of data collection that one would engage with user-generated data to top up the data gaps?
Yeah, I think that sort of, it's almost citizen science, isn't it? The sort of like farmer-based science would be really useful. A colleague of mine is developing an app at the James Hutton Institute in Aberdeen. It's developing an app where you can take just a photo of the soil and it will give you an estimate of the soil type. It geolocates it on a soil map and it tells you what the characteristics are likely to be given the photo and given the underlying data. But at the moment, that's just being used to tell the farmer, who's got the app, what the soil type is like. If we could then upload that data and start to use that, collect that in a database, that would give us great strength going forward to combine that with spectral library data. So where spectra have been taken of those soils or soil types that are closely related to it, we could start to gain information about just by taking photos and by collecting other information about the soil, we could get a better estimate of the baseline conditions of those soils. So I think that's got great potential.
Okay, let us know when that app is ready, because we're going to the field next year, hopefully.
I'll send you his email address after, Jan. Yeah.
Perfect. Philippe, you want to tell that your question by yourself?
Yes, sure. Thank you for the presentation. My question is about what's the average depth? You showed some potential sequestration. What's the average depth? And also, which are the implications of including deep soil carbon sequestration in this magnitude and also in the models?
Great question, Philippe. So most of the soil organic measurements have been taken 0 to 30 centimeters. There are fewer deeper samples down to 1 meter, and still fewer down below 1 meter. So most of the soil carbon maps contain soil profile data down to 1 meter. And generally speaking, in agricultural soils, about half of the carbon is held in 0 to 30, and about half of it is held between 30 and 100 centimeters. But recent studies have shown that carbon that's held in the lower soil turns over slower. So a small percentage of that is carbon that's been fixed in the last 50 years. So that tends to be the slower turning over carbon that's more important on longer time scales. But it's an under-researched area, and I think one that's been the Cinderella in a way of soil carbon research. It's much easier. We've had the idea since we started soil science that all of the action is in the top, and most of it is. To a certain extent, that's true. But that means that we've neglected the deep soil. And I think there is much more information that we could get on deep soil. And it could turn out to be very important in terms of climate change mitigation.
And your hand is still up. Is that, you have a second question? No, okay. Maybe then I add an own question, Peter. Where do you think is the biggest need in I'm talking about the scale of observation. Which scale do we need to improve to look more into hotspots that drive the global carbon models, or do we still lack too much of the area information? I'm talking about global carbon soil models, not about local ones.
Yeah, so globally, I think it's fair to say that we can concentrate on hotspots. We know that we can gain soil carbon in mineral soils of, say, up to 1 ton per hectare per year. But we know that a degraded peatland loses 30 tons per hectare per year every year, and that will continue happening until those peatland soils are re-wetted. So we already know that there are some soils which are hotspots of carbon loss, and we also know from land management, as I said, cropland soils are depleted in soil carbon. They tend to be, and particularly in the tropics, those tend to be losing productivity. They're then abandoned, and that can lead to further land use change. So I would say 2 areas to focus would be one on protecting the soil carbon that we've got in our very high carbon soils, peatlands, and we need a better mapping of peat depth. We've got really poor maps, even within country, of peat depth and peat carbon stocks. So that we could certainly do with better mapping of those, but also better mapping, fine scale mapping of the land use and how the land use has changed over time.
Yeah, thanks. Monica is your next.
Yeah, thank you very much for this very interesting and inspiring talk. I was wondering, you mentioned at the beginning some costs of carbon sequestration, and then listening to you further on, I was assuming that probably those costs which you mentioned did not include the cost for monitoring, reporting, and verification, and it probably is much, much higher if we would include those. Is that correct?
Yeah, that's quite right. I think it's soil carbon sequestration, because the monitoring component has not been considered really in terms of projects, you know, measuring soil carbon at a project. The MRV costs haven't been considered in those carbon costs. So the costs that I mentioned include the cost of doing a practice, you know, the opportunity cost that of not doing something else, and the cost of changing your the method of tillage. So you have if you have to buy new machinery, you have to buy direct drill machines, for example. It includes all of those costs, but it doesn't include MRV. So MRV could potentially be quite low cost if it was done through remote sensing, through activity data that was collected from farm records and through models. But at the moment, MRV costs are very high, because it relies on lots of soil samples, lots of laboratory analysis, and it's very labor and cost intensive. I think if you included those costs, then it becomes much more costly. That's a good point. I'm glad you pointed that out.
Yeah, thank you. Gabriel again.
Yeah, I would like to have one small follow-up. You mentioned that restoration of wetlands and peatlands will help to increase soil sequestration. I just wonder, aren't there also instances where actually like turning land into wetland could also actually do the opposite? Because I mean, imagine you have this increased microbial degradation that then will lead to carbon losses. Are there studies where this has been shown as well? And what would one have to take into account then?
Yes, you have. Your colleagues in Greifswald have done a lot of work on this, Hans Houston, looking at particularly the methane emissions that you get after rewetting, and weighing those up against the carbon losses that you had before rewetting. And you can get a significant pulse of methane, but that tends to be short-lived, and it depends on the type of wetland that you're talking about. The fens, which are fed by water from surrounding agricultural land, are nutrient rich, and they can lose really significant amounts of methane and nitrous oxide when they're rewetted. The upland peats, the ones that aren't surrounded by agricultural area, the methane emissions tend not to be very large. So that tends to be a smaller peak, and it tends to be shorter lived. It's something that has to be considered, but in the long term, when the system settles down after that peak of emissions declines, the net balance is again positive. So after maybe 20 years or 30 years, you're back into credit in terms of the net greenhouse gas balance.
Thank you.
Any more questions? Maybe then I ask a second one, if I may, while you think of. I would like to come back to the slide with the zero sequestration potential of the manuring. There are other scenarios where parts of the manure is put to the grassland and you put it to soil instead, or you take it away from a soil with high carbon saturation to soil with a low carbon saturation, or you split concentrations. And then likely the potential is not zero. I don't know about the transport costs, which would which would change it again. But yeah, have you any idea about the magnitude or potential which could be taken from that?
Yeah, that's true. Yeah, so that was just a thing saying if you're moving it from one bit of cropland and putting on another bit of cropland and only measuring one, you're going to get you're only measuring one side of the equation. That was the point of that slide. But you're quite right. If you take it from a saturated system, like grasslands tend to be close to saturation, and you put it on a cropland, then you're likely to get much more carbon sequestration on that cropland. On the transport issue, I did a paper in Ecology Letters with my dad on this issue. My dad is a lorry driver, and we did some calculations together because he knew all about the size of trucks. So in the pub one night, we did some calculations on what distance of travel by lorry you would have to move manure before you lost the carbon benefits. And we managed to publish that in Ecology Letters. To my knowledge, that's my dad's only paper. Oh. But he is a lorry driver.
Yeah, we'll check that. Thanks. Any more questions? This does not seem to be the case. There was a very interesting discussion, as interesting as the talk, I think. You had a very broad audience, Pete, from soil science to economy and from macro to microeconomy. So I think it was just inspiring for all of us. Thank you very much.
Thank you for having me.